It is my pleasure to introduce Randy Grace, who's going to talk to us this afternoon about statistical methods and data analysis. And I guess the basic message is that numbers are your friends. And there is a great deal of delight to be derived from just ordering numbers in ways that reveal sometimes just magnificent structure. And you can't do that very well with words. Words are much tougher. But numbers are your friends. Randy got his PhD at the University of New Hampshire, working with me in 1995. I guess it's been 10 years, just about, that we've been working together. Randy moved to New Zealand in 1998, where he is now senior lecturer at the University of Canterbury, Christchurch, New Zealand. One of those marvelous places, both in terms of the people, the countryside, and the intellectual life and quantitative analysis of behavior. Randy?
Thanks. Okay, scientists make extensive use of models to describe and understand their data. In last year's part 1 of the tutorial on quantification, I talked about how significance testing could be understood as model comparison. That is, in the simple t-test, you've got a choice between one model that says that the populations corresponding to the two groups have different means. This is your research hypothesis. And you have to choose between that and your null hypothesis, which holds that the two population means are the same. In fact, any hypothesis test that you do based on the general linear model can be construed as a choice between two models. What we're going to do today is consider some techniques for model selection that really go beyond, sort of go out of the box of straight hypothesis testing. And we'll start by considering a case study in exploratory data analysis, and then the most important thing you need to know about model selection. And I promise you will leave today with that principle firmly grasped. And then we'll do a model selection case study. Okay, well, what is exploratory data analysis? Well, it's actually rather difficult to define precisely. And this is because the methods that you use often depend on the particular problem. So exploratory data analysis is overall a flexible approach to data analysis. The data analyst, he or she is like a detective, sort of sifting through clues, trying out different ways of looking at your data, trying to make the data tell a story, trying to understand the set of data that you've collected. There's an extensive use of graphical methods and a use of robust measures, such as the median, non-parametrics, robust measures that might be more resistant to outliers or extreme values. And EDA is characterized as an iterative process of model building, analysis of resulting errors, and model respecification. That sounds like a lot. Basically, in plain English, that means you formulate a hunch, you try it out. If it doesn't work, you try something else. That's basically exploratory data analysis. And so what I'd like to do is consider a very simple case study in exploratory data analysis. This is air quality in Christchurch, New Zealand. The data are fictional, but the situation is actually real. Christchurch, there are many wonderful things about Christchurch. One bad thing is that there's a smog problem during winter. So imagine that you've been hired as a consultant to the Christchurch City Council, and they want to know which of two instruments for measuring air quality they should purchase. And you've got some data. Air quality has been measured by each of these instruments over 50 consecutive days. And your job as consultant is to tell them which one they should choose. So the data that you have are quite simple. You just have 50 numbers over successive days for instruments 1 and 2. And we can assume that higher values mean poorer air quality. So, okay. Now, you're no environmental scientist, but one thing that you should always do, a good exploratory data analyst, before you plunge ahead into trying different ways of analyzing the data, different ways of plotting the data, you need to stop back and think. And what do I mean by think? I mean consider what it is that you're looking at and try to come up with some different possibilities. As far as air quality goes, you know, as I said, you're no environmental scientist, but let's think about it for a minute. Either air quality is something that doesn't change from day to day. So the true value of air quality, assuming there is something called air quality that can be measured, either it's constant each day or it's changing. Now, if air quality is constant, you still wouldn't necessarily expect the measurements returned by the instruments to be constant because you don't expect the measures to be completely reliable. That is, there's some measurement error. And so we can generate a model for the data in that case. Each observation should be giving us a measure of true air quality plus some error, just plus some random error in the measurement. That's one possibility, perhaps not very likely. The other possibility, which maybe is more likely, is that air quality is actually changing. So true air quality varies from day to day. In that case, each observation can be modeled as an overall average air quality score plus some difference that depends on the particular day at hand, plus your error measurement. So these are two possibilities regarding air quality. And what we're going to do with our exploratory data analysis is try to decide if we can choose one or other of these models. Well, the first stage of exploratory data analysis is always to look at your data, to just examine your data. So what I've done is simply display a histogram for the observations of instruments 1 and 2. And if we look at the top one, the top panel, we can see that the observations are approximately normal. There seems to be a clear peak around 275. Perhaps there are 2 extreme points on the high end. We would say that these data are roughly normal, perhaps with 2 outliers. As far as instrument 2 goes, which is the bottom panel, we can see that the data do not look so symmetrical. Instead, the histogram appears to be negatively skewed. There seem to be a lot of observations bunched up at the high end. So perhaps our first clue, again, thinking about the data analyst as a detective, you just have to note these clues. It looks like the 2 distributions do not have the same form. Another technique for displaying data is to form box plots, is to show box plots. Now this basically shows generally the same information that you get in a histogram, often in a form that's a little bit easier to digest immediately. The upper panel again shows the distribution for instrument 1, and you can see that with a box plot, you've got the box, which here notes the difference between the 25th and 75th percentile scores, and the median appears as the tiny little box within the box. The whiskers show the range of the data that are not classified as outliers. And the outliers of the 2 extreme points are shown as individual data points. So we can see that the data for instrument 1 look approximately normal, except we've got the 2 outliers. For instrument 2, there are no outliers, but you can tell that there's negative skew because the location of the median relative to the full range of the data is closer towards the top. So that's saying that the data have negative skew. Okay. One other thing that's usually good to do is simply look at the mean and the median, standard deviation, look at the descriptive stats for your variables. And in this case, we see that the average observation for instrument 2 is slightly higher than that for inst 1. but the range of scores, the minimum score for instrument 1 is 1, maximum is 625, and the standard deviation is greater. So it looks as though instrument 1 may be more sensitive, but at this point we don't know whether or not that means anything. Again, we're just at this stage of the analysis, we're just looking for clues. Okay. Now, the observations that we have form a natural time series. That is, they were recorded over consecutive days. So as you're thinking about it, one simple technique to try would be simply to plot the observations for each of the instruments as a function of trial. And that's what I've done here. This would show, for instance, if one of the instruments broke or deteriorated in some way over time, you might see some kind of change. And in fact, it looks like there's not much going on. We don't see any kind of a trend in the observations for either inst1 or inst2. So to summarize so far, it seems like we've got basically two clues that the data for instrument 1 are about normally distributed with two extreme outliers on the high end. The data for inst2 show negative skew, and not quite sure what to make of that yet. At this point, it might be a good idea to think about the two possibilities that we mentioned at the outset, our two models which we're going to try to choose between. Either air quality is constant or air quality changes from day to day. Now, in the latter case, if air quality is in fact changing, then on a relatively poor day, you would expect both instruments to have high values, and on a relatively good day, you would expect both instruments to have low values. That is, there should be a correlation. There should be a positive correlation between the measures if air quality is changing. So how do you look for a correlation? You make a scatter plot. And this shows a scatter plot of observations of inst2 versus inst1. And aha, we notice that, in fact, there is a clear positive correlation. The data are going up from left to right. This tells us straight away that the measurements of air quality appear to be valid. That is, air quality seems to be changing from day to day. Both instruments are telling us basically the same thing. But if you look at the graph carefully, you'll notice it tends to flatten out. That is, as scores for inst1 become very high, in fact, notice the two extreme points way on the upper right-hand corner, it looks as though the observations for instrument 2 are flattening out. This suggests that instrument 2 has a ceiling effect. Basically, as air quality gets really poor, instrument 2 reaches a maximum, whereas inst1 is able to remain sensitive to very, very poor levels of air quality. So at this point, it looks like we're going to recommend to City Council that they purchase inst1. But there's one more technique that we might want to try before we do that. And this is something that's very useful to do with a scatter plot. The upper panel just shows a regression line fitted through the data. That's a little bit hard to see, but the slope of the regression line is shown there. It's 0.7. So this means that for a 0.7 change in inst1, rather for a unit change in inst1, we get a change of 0.7 in inst2. And that means over the full range of values, instrument 1, in fact, is more sensitive than inst2. The bottom panel shows another technique that's useful when you're making this kind of scatter plot, and that's just to show a line of equality. Now, when you superimpose the line of equality, that means that if the two instruments agreed in their measurements, all of the points would fall exactly on the straight line. And in this case, what you'll see is that from about 0 to up to about 350, the data points appear to have a slope that's roughly parallel to that straight line, but they're displaced. They lie above the line. This suggests that over that range, for a 1 unit change in instrument 1, there's a 1 unit change in instrument 2. That suggests that over that range, the two instruments, in fact, agree in terms of their measures of air quality. But the displacement, the fact that the points lie above the line, suggests that the instruments might be calibrated in a different way, with the overall values for inst2 being a little bit greater. So, what do we conclude from this simple exercise in exploratory data analysis? Well, overall, a positive correlation between the measures suggests that our second model, that air quality in fact does vary from day to day, is the correct model. For a fairly wide range of values, the instruments are linearly related with a slope of 1, with the points lying above the line of equality, suggesting that over that range they do agree in their measurements, but are not calibrated the same way. Flattening out of the scatter plot suggests a ceiling effect for inst 2. And finally, the histogram for instrument 1, being normally distributed with 2 outliers at the high end, suggests that air quality is normally distributed with the occasional exceptionally bad day, which I can tell you is true for Christchurch. So this example illustrates that starting from basics, I mean, we didn't do anything fancy. We simply used different ways of plotting the data. We can make the data tell a surprisingly rich story. This is the goal of exploratory data analysis. And I also would like to point out that formulating the different possibilities in terms of models, that is a question of whether air quality was constant or changed from day to day, when we formulated that in terms of models and then thought, well, how can we test those models? That led us to the idea of looking at the scatter plot, which was the key, really. So the point here is simply that it's important to think about what it is that you're trying to understand and then use different types of graphical methods that might help you answer those questions. But sometimes the models that we're trying to compare are not so simple. With the exploratory data analysis, we just plotted the data and it all fell into place. Sometimes things can get more subtle. And so consider the following thought experiment, which will lead us to the most important thing that you need to know about model selection. Now we're talking about models that can be quantitative models with different numbers of parameters that we might have to fit to the data. Let's assume that we've collected 20 data points and 2 models have been fit. Model 1 is more complicated, has 10 parameters, but it's accounting for 99% of the variance. Model 2 is simpler, has 3 parameters, but it doesn't do as well. It accounts for 90% of the variance. So here's the thought experiment. If we replicate the experiment, in other words, we go and collect 20 new data points, and the new data are fitted with the parameter estimates from the original data, then which model, Model 1 or Model 2, will account for more variance in the replication data? That's the question. So it's really a question about model selection. Which of the 2 models is to be preferred? And you can see that there's going to be a trade-off. Model 1 is doing a better job in terms of variance accounted for, but the question is whether the additional 7 parameters, 10 parameters versus 3 parameters, whether those additional parameters are justified. Now, if these models were nested, in other words, if Model 2 was a special case of Model 1, you could perform a hypothesis test and find out whether or not the increase in variance accounted for, that 9%, was a significant increase. If the models were not nested, you could use something like a model selection criterion, such as the Akaike information criterion. We'll see an example of this later on, to basically make the same decision. But in order for us to have some feeling for this thought experiment, we need to get into the issues a little bit more deeply. And to do that, I'd like to consider the following example. Now, this is simply a distribution of ages in a population of a city, 20,000 people. And let's assume that these 20,000 people, this is all that we need to know. We have the ages. And what we're going to do is try to model the distribution of ages with 2 models, with 2 competing models. The models are simply histograms. And the first model is a histogram that has 45 bins, and the second model is a simpler histogram that only has 9 bins. So what I've done is calculate the 45-bin and 9-bin histogram that accounts for the most variance in the population data. So these are the best possible 45 and 9-bin histograms that we can ever find. And I'd like you to think about this because these models, the 45-bin and 9-bin models, are actually classes of models. And the particular 45 and 9-bin models shown are the best exemplars of each of those classes that can ever be found. In other words, the population of 20,000 people is reality. That's truth. That's what we're trying to capture with our models. We have a 45-bin model that clearly does a better job of capturing all the subtleties in the population than our 9-bin model does. But the important thing to remember is that for both the 45-bin and 9-bin models, these are classes of models, and these are the best examples of those classes that we can ever find. However, whenever we look at models, we usually, if we're trying to evaluate models, we never know the entire population. Instead, we have a sample. We have a sample of scores. We have a sample of behavior. If you think about it in terms of applied work in applied settings, you want to know whether some intervention is effective. You're not going to be observing your clients 24/7. You'll have a sample of behavior. And this shows a sample of 200 people, 1% of the original population of 20,000. And so what we want to do is imagine that we're going to be comparing our two models. And so what do we do when we compare models? Well, we fit them to sample data, and then we see how well they perform. So here we see our 45-bin histogram, that is the best fitting 45-bin histogram to the sample of 200, and also the best fitting 9-bin histogram to the same sample. Now, the variance accounted for by the 45-bin is clearly going to be better. It does a better job of tracking the peaks and valleys in our sample. And so if we ask ourselves, and of course this is the question that we always want to ask, which model is better? If you simply look at variance accounted for, you'd likely consider that the 45-bin model is doing better. But there's another way to think about the adequacy of the model, and that is in terms of how close the models that we're estimating based on the sample are to the best models in their respective classes. In other words, from a statistical point of view, what we're doing is using our sample to estimate parameters for these classes of models. And one way we can ask about the adequacy of these models is to look at how well they describe the sample data, but another way is to look at how close they come to the best models in their families. Now, because this is an example that I've made up and we know what the population is, it's possible actually to compare the 45-bin histogram that we estimated to our sample with the best fitting 45-bin histogram for the population. And if you do that, you'll notice that it actually is all over the map. There's a pretty great discrepancy between the 45-bin histogram that we fitted to our sample compared with the 9-bin histogram, which, as you can see in the lower panel, actually comes rather closer to the best member of its class. So if we ask ourselves what's the best model, there are two ways of thinking about it. Either we can look at how well it describes the sample data, or we can consider how close does it come to the best possible model of its class. Well, this illustrates something called the principle of parsimony, which in fact is, ta-da, the most important thing you need to know about model selection. What is it? Well, more complicated models, that is, models with a greater number of parameters, are susceptible to a problem called overfitting. That is, the parameter estimates may be influenced by noise. In this example, we had a population of 20,000, a sample of 200. There were some peaks and valleys in our sample that were not representative of the population. Because of the additional flexibility of the 45-bin model with all of its parameters, those parameters were reacting to the unsystematic variation in our sample. So that means we want our models to be as simple as possible. The 45-bin model was too complicated for our sample. But on the other hand, if we have a model that's too simple, we may fail to capture structure in our data. So a model with only 9 parameters may actually not be able to capture all of the information that actually exists. And this is a problem called underfitting. So there's a trade-off between the complexity of a model and this tendency to over or underfit the data. In other words, you want to have a model that is just complicated enough to capture all of the meaningful structure. But you don't want it to be too complicated, because if it is, then the parameter estimates are likely going to be affected by noise, and you'll have the problem of overfitting. So this is called the principle of parsimony, and in fact, it's the most important single thing to know about model selection. Well, let's get a little more, try to tie these concepts together. What happens? What's happened here when we've compared different models that have been fitted to the same data, the same sample? Well, we're assuming that there's something out there, that the truth is out there. There is a possible most accurate model. We call this a generating or operating model. In this case, we knew the distribution of the 20,000 ages within the population. For each model that we're going to compare, there's a single best model that is the closest approximation to truth in that class of models. So we had our 45 and 9-bin models that were fitted to the population. We call these the best approximating models. But what we have to compare, what we have to make our decision on the basis of, are the models that are actually fitted to the sample data. We call these the estimated models. That means we have 2 sources of error or discrepancy in our fitted models between truth and the best approximating model for the particular class, and between the best approximating model and the estimated model. So we can say that the overall discrepancy in a model that's been fitted to a sample is the sum of the discrepancy in approximation, that is, how much of truth does the class of models fail to capture, plus an estimation discrepancy, which is how far the estimated model deviates from the best approximating model in its class. Now, there are numbers that you can compute which are statistics that allow you to estimate the overall discrepancy. And these numbers are called model selection criterion. Model selection criteria. Probably the best known example is the Akaike information criterion, or AIC. Now, I have to apologize for showing this equation. I wanted to have this be an equation-free tutorial, but don't worry about it. It's actually, the structure of it is fairly simple. On the right-hand side of the equation, there are 2 terms. The first term basically is a measure of goodness of fit, and the second term is a penalty term for the number of parameters. So AIC embodies the principle of parsimony because it rewards a model for how well it's fitting the sample data, but then at the same time it penalizes more complicated models by having a penalty term. And with AIC, you compute the values for each competing model, and the model with the lowest AIC score is the preferred model. Now, there are other model selection criteria besides AIC that have been used. There's some based on Bayes factors and so forth. But they're all based on the same principle of parsimony, and the idea that the overall discrepancy in a fitted model is your approximation discrepancy plus the discrepancy because of having to estimate the model to a finite sample. So if we go back to our thought experiment for a moment, which model is going to account for more variance in the replication data? Model 1, the more complicated model with 99% of the variance accounted for, or Model 2, the simple one with 90%? Well, we can't tell for sure because, let's face it, the more complicated model may actually be true, and if you replicated, maybe again, you'd get 99% of the variance. But I think your best bet would be Model 2. That is, it's very likely that Model 1 in the original sample with its 10 parameters, those parameter estimates would have been affected to a greater extent by noise. It's probably overfit. So that's the principle of parsimony. Okay, well, in the final section of the tutorial, what I'd like to do is show you a case study in model selection. And these are real data, come from the area of temporal discounting. And Leonard Green gave an outstanding tutorial on temporal discounting as part of this general series last year. In fact, the first data that I'd like to show come from a study of his, Green, Fry, and Meyerson, 1994, and they determined the present value of hypothetical $1,000 and $10,000 rewards, which were received after delays ranging from 1 week to 25 years. Now, in temporal discounting, the present value is the amount of money available immediately that's judged as being equal in subjective value to the delayed amount. And it's usually expressed as a proportion of the delayed amount. So the general phenomenon, which has been found in many studies, is that as the delay increases, the present value of the delayed reward is decreasing. And at issue is the precise nature of the mathematical function that describes that decrease in value over time. So what quantitative model will provide the best account of data from temporal discounting studies? Well, I just looked at 3 simple models. The first model is the most widely used model of discounting, a simple hyperbola proposed by Jim Mazur. The second model is a generalized hyperbola, basically a simple hyperbola with the denominator raised to an exponent. And the third model is just a power function. And there were 20 data sets from 9 studies which I obtained for this analysis. The approach was to fit each model to all 20 data sets. And I used multiple criteria to evaluate the models, including variance accounted for, the Akai scores, and also analysis of residuals. So just starting with variance accounted for, the models all did really well. Averaged across the 20 data sets, the simple hyperbola accounted for 94.6% of the variance, the generalized hyperbola 97.6%, and the power function 95.9%. So all the models are doing extremely well. Based on variance accounted for, it looks like the generalized hyperbola might be the best. It's got an increase of 3% in variance accounted for, but the question is whether or not the additional complexity of the exponent in the denominator is basically worth the increase in variance accounted for. And so the Akai criterion, because it embodies the principle of parsimony, we have a way of trying to quantify this trade-off between the goodness of fit of a model and its complexity. What I did for the Akai analysis was to compute the AIC scores for each of the models, for each of the fits, and then score a win for a particular data set when a model had the lowest AIC score. And when I carried this out, the simple hyperbola had the lowest AIC score in 16 out of the 20 data sets. So the Akai scores are telling us that the additional complexity of the 2-parameter models, because both the generalized hyperbola and the power function have 2 fitted parameters compared with 1 parameter for the simple hyperbola, that additional complexity seems to be unnecessary. The third analysis that I carried out was looking at the residuals. Residuals are what's left over in the data after you've made the predictions with your model. And the idea is to see whether or not there's systematic errors made by a model when it's fit to data. Residual analysis is based on what John Tukey, the founder of exploratory data analysis, called the fundamental equation of EDA. Data equals model plus error. If you subtract model from data, if you subtract the prediction of a model from data, what you're left with is error. And that should be just white noise. It should be normally distributed. It should have nothing systematic at all. If there are systematic errors, in other words, if your residuals are non-random, then that implies that there's structure in the data that are not accounted for by your model. So the idea with residual analysis is to see whether or not there is some structure. There might be something that the models are not actually able to pick up. So what I did was simply calculate the residuals for each of the models for all 20 data sets, and I pooled them. And there are a number of ways that you can look at residuals. You can examine them for normality. You can look for outliers, extreme values. One common technique is to look at the relationship between the residuals and the observed values. And on the left panel, I've shown just some hypothetical data in which the predictions of the model are shown with a solid line. And if I plot the residuals against the observed values, as shown in the right-hand panel, you'll see that there's a negative correlation. Where's this negative correlation coming from? Well, what's happening is that the model is making systematic errors. For very high observed values, the model tends to predict values that are too high. That means that the residuals tend to be negative because the residuals are defined as the observed values minus the predicted values. But for low observed values, the predictions of the model tend to be underneath. So the model is underpredicting for lower values. This produces a negative correlation if you plot the residuals against the observed values. Now you can also plot the residuals against the predicted values and various other types of plots, but this is one that I thought I would start with. So when we look at the residuals pooled for the simple hyperbola, in fact we do see a statistically significant negative correlation. So we see a correlation of minus 0.43. This suggests that in fact the simple hyperbola is tending to underpredict high values and overpredict low values. For the generalized hyperbola, the residuals don't show any kind of linear correlation, but there seems to be, in fact, something non-random. It looks like there's a kind of curvilinear relationship, sort of an inverted U-shaped function. Actually, when I first saw that, I thought it looks like Australia, which is actually something very bad if you're in New Zealand. But anyway, this also looks like there's something non-random. And this particular pattern would mean that for low observed values and for high observed values, the generalized hyperbola is overpredicting, but for medium values, it's tending to underpredict. So it's a rather complex type of pattern, but the presence of anything non-random within the residuals is like a signal that there's something not quite right with the model. And lastly, for the power function, it looks to me like it's very, very non-random. Very, very random. I couldn't detect any type of pattern. There seems to be one outlier down at the bottom, but overall, it just looks like a point cloud. So I would say that there's no relationship in that scatter plot. So what are the conclusions from our case study? Well, with the residual analysis, the simple and generalized hyperbolas apparently failed to capture some structure in the data, as evidenced by a pattern of residuals that was non-random when plotted against the observed values. The power function showed no systematic error in the same analysis, and so according to residuals, the power function was performing best. According to the Akai-K criterion, the simple hyperbola was the best model. But according to variance accounted for, generalized hyperbola accounted for the most variance. So we have three models, we used three different criteria, and we had three winners. Well, I told you I didn't make these data up. And this is, in fact, what often happens. We can't really come to a clear conclusion on the basis of this analysis. In fact, this illustrates the importance of using multiple criteria. If you use multiple criteria and no single model emerges as the winner, then very likely we don't have enough data yet in order to come to a clear picture. If the simple hyperbola had performed best on all three measures, then we might be in a position of being able to say with some certainty that it was the preferred model. It is very important when you're doing this type of exploratory work. It's very important to use multiple criteria when you're choosing among models. For temporal discounting, these results might be taken to imply that the differences among the models are subtle. And let's not forget that each of the models was accounting for well over 94% of the variance overall. So we're really trying to split hairs here. It means we need more data. And it's also possible that some alternative model, other than the three that we considered, would perform better. So if we sort of step back and ask ourselves, exploratory data analysis, model selection, what does all this mean? Well, models are like milestones on the road from data to theory. Scientists develop models to try to describe their phenomena and then formulate theories to explain those models. So model development, comparison, and selection are critically important for any quantitative science. And it seems like the best way to do this, the best way to evaluate models, is to use multiple methods in the overall framework of exploratory data analysis. And if there was one thing I'd like to say to students especially, this is what I always tell my own students, data analysis isn't boring. And why? Because in exploratory data analysis, you're like a detective sifting through clues. You're making the data tell a story. The clues are like pieces of a puzzle, which when you put them all together, they should tell a story. Science is really like a game. It's a very serious game. It's a very important game, but it's still a game. And that means that you should have some fun. So next time you sit down to do some data analysis, have some fun with it. Thank you very much.
Questions?
Peter. Randy, I really enjoyed your talk. Thank you.
Okay.
In the case study, did you fit individual subject data or pool data?
I looked at both. I looked at the individual data for some selected studies, and I didn't look at all of the studies, and so I can't come to any strong conclusions, but I am not convinced that the same pattern of residuals necessarily holds for the individual data. So I think that the problems with the hyperbolas may have to do with averaging data, but I'm not sure about that yet.
Again, to ask another question about specific what did you do about the amount effect? What did you do about the
Right. Yes. How he's asking, actually, if you could put the overhead back up, there's the first one that I had with the Green, Fry, and Meyerson data. How he's asking, what did I do about the amount effect in the temporal discounting data? This is the phenomenon that for larger amounts of money, the discounting rates are lower than for smaller amounts of money. Yeah, and so you can see that for the $10,000 rewards, the present values are greater as a proportion of $10,000 than the $1,000 rewards. The answer is that and actually most of the data sets that I examined used different amounts, and so this effect was present in almost all the studies. I simply used different discounting rates for the different amount conditions. So I basically added a parameter, but it didn't, because it didn't affect the structure of the model. And the factorial design used in the experiments, it basically just gave me twice as many data points.
My question is simply this. How do you know, this is a meta question, how do you know when you've got enough data, when you can stop collecting data? It clearly isn't when all these multiple criteria focus on one thing. It could still be, if you collect more data, they'll come apart again. So what's the criterion there?
Well, I have to say this. You've probably got enough data. Michael was asking, when do you know when to say when? How do you know when you've got enough data? This is a very, very hard question to ask. And actually, the case study the example that I presented with the age distribution and having a sample of 200, a model with 45 parameters was more susceptible to noise. So it was overfit to the sample of 200 compared with the 9-parameter model. If you had a sample of 2,000 rather than 200, the 45 bin model probably would have turned out better. Probably would have been the preferred model. So I haven't been able to find any clear answer. You need many more data points than you have parameters.
So
Sorry?
So work on it.
Well, okay. Russ.
As an alternative to these criteria like Ekaki or Bayesian one, what is your feeling about estimating the parameters on one sample and using them on the other half?
Right. The question is, rather than using model selection criteria like AIC, what happens if you estimate the parameters with one sample and then you test those parameters using a different sample, using an independent sample of data? This is called cross-validation. It's actually was behind my thought experiment, the idea that you can take these two models which have been fitted to one set of data, now you've got essentially fixed parameter models, and you apply them to a new set of data, which one's going to perform better. It turns out that cross-validation, there are ways of using Monte Carlo and sort of bootstrapping techniques. If you have, for instance, one large data set, you can break it into many possible halves, and you estimate the parameters in one half, and then you use those as fixed parameters and see how well it describes the data in the second half. If you do this for all possible splits, you can form a distribution, basically, of variance accounted for. And when you do this, it turns out that the models that perform best according to that kind of analysis also perform best on the AIC. I think Michael Brown, there was actually one thing I should have said. A lot of my talk, a lot of the ideas were taken from an excellent special issue in the Journal of Mathematical Psychology, which appeared in 2000, the results of a symposium that were held, I think, in Indiana University. So I strongly recommend anyone who's got an interest in model selection to look for that special issue. But basically, cross-validation turns out to give the same answer, at least in the Monte Carlo studies that have been done, as the AIC and the other model criteria.
Another criterion for choosing between models is not strictly a statistical one, but if you think of what the interpretation of the parameters are in the models that you're using, and the vulnerability of each different model to empirical research, experimental research, that the parameters might not be benefited, then you might prefer one model to another simply because it's a better guidance for future research.
That's an excellent point. Alex is saying that in some cases you might choose one model versus another, not on the basis of some number like the AIC, which we're computing, but on the basis of how much conceptual or theoretical sense the parameter values make. And that underscores, I completely agree with you, that underscores the importance of scientific judgment when you're looking at the question of model selection. And one point that needs to be made is that there is no royal road to inference in all of this. There's no magic way to choose between models, as it were. You can never get away from the importance of scientific judgment. And so I think that that's basically what you're asking. Yeah.
Same question. Others?
A related point to Alex is actually in thinking about what comments you made on your very last slide, where you said that models can often give rise to theories. How often do you think it happens in that direction versus the other way, where theories give rise to models and we have sort of empirical grounding for what the parameters mean going in, and then instantiate them quantitatively?
The question is, how often do theories sort of emerge from the ground up, as it were, that you collect empirical data, develop models, and then try to form theories which are able to explain those models? Compare that with how often do you get models which basically emerge from theories, sort of a top-down as opposed to bottom-up. I don't have a clear answer for that. I think it sort of depends on what philosophy of science you might subscribe to. Certainly behavior analysis has been influenced by Ernst Mach and from sort of a positivistic empiricist approach. It was kind of probably evident that I hold that kind of a view based on the way I was talking here. But the idea is that you start with empirical data and then form models, and then theories emerge out of those models. But I think in some cases you can certainly physics, you had the development of non-Euclidean geometries, which then led to theoretical and empirical developments in modern physics. So I think there are some examples of top-down as opposed to bottom-up. I don't know which is going to work better for us. I think you have to be open to either.
One more? Just to build on what Alex remarked, one of the problems that we have many times in contrasting models is that we don't have theories of the parameters. They are just free, we have no clue. So a different strategy might be to try to find what is distinctive about each one. What sort of is the signature of the model? And for example, with some analysis, you might find that they are similar in the central region of the data, but very different in the tails. And that suggests experiments where, I'm speculating, the delays are pushed to the limit, and then the models start to make it predictive. So find regions where the discrepancy between these models are bigger. And so that would be an interchange between analysis and then empirical stuff.
I think that's a really good point, and as models become more sophisticated, and we are starting to split hairs, I think being able to use the incredible range of software tools that we have available. I mean, even something as simple and widespread as Microsoft Excel really is just tremendously powerful in terms of being able to generate predictions of very complex models over a wide range of parameter values and be able to basically explore the behavior of our models. So instead of just the old analytical tools solving equations and so forth, we now have at our disposal computational resources which allow us to analyze functional behavior of models.
Randy, thank you.